Let's consider the example when f of z is equal to 1 over z times z minus 2 to the power of 4. We can write it in this way as well. And we are now going to find the residue at the following singular point, namely z0 equal to 2. We obviously see that this function has two singular points because the denominator is 0 when z is equal to 0 and z is equal to 2. So let's try to find the residue at the point z0 equal to 2. In order to do this, we have to find the Lorentz series around 2. And we know that this Lorentz series looks like this. We have all these an coefficients and all these bn coefficients here, this principal part of the Lorentz series. And we are now interested in finding this coefficient. So let's first find the Lorentz series of this function. First, we observe the following. If I find the Lorentz series of this function 1 over z, it also looks like this. So by multiplying this Lorentz series with z minus 2 to the power of minus 4, I obtain a new Lorentz series. So we do not need to do anything about this term. It's enough for us to first find the Lorentz series expansion of this factor and then multiply this series with this guy. Okay, I've done this trick many times before. It's a little bit difficult trick, but I'm doing it once more. 1 over z can be written as I want this to be some series in the powers of z minus 2, and I know this from before. This will be a geometric series if I just change it, the denominator, by z minus 2, and I must add 2 because otherwise I don't get this equal to z. So I'm doing this trick. Now I realize that in order to obtain a geometric series, or the limit of a geometric series, which I know the formula for, I need the number 1 in the denominator. I don't have it, so then I divide by 2 in the above and below. So therefore I get 1/2 here, and this I can lift in front of the fraction, and then I obtain this result. Now I see that I have some 1 plus a variable here. In the formula for the geometric series, I need a minus here. So therefore I take a minus here, and in order to obtain equality, I have to compensate this by multiplying with minus 1 on this part. But now I see that this is the limit of a geometric series where this guy is the variable. So this is just equal to 1/2 times the geometric series minus 1 to the power of n times z minus 2 over 2 to the power of n. So, well, I can now multiply with each term with 1/2 or 2 to the power of -1 if you like. And then I obtain this coefficients. So now I have the Lorentz series for the function 1 over z. We see here that we have z minus 2 to the power of n in each term multiplied with some coefficient. Moreover, we can take a look on the convergence domain. We know that this u should have absolute value less than 1. That's generally for any geometric series, and multiplying with 2 on both sides of this inequality, we obtain that the absolute value of z minus 2 should be less than 2. So this means that we have a series expansion which is valid inside this circle, centered at 2 and with radius equal to 2. We cannot go out of this circle because we have a singularity here. Okay, now I'm reaching the goal very soon because I have this expansion for 1 over z, which is this expression multiplied, and I can multiply each term by 1 over z minus 2 to the power of 4. This was the original function f of z. So I now just multiply each term in this power series with z minus 2 to the power of z minus 2 to the power of minus 4. Then I obtain this series. And it's always useful to write down some terms of this this infinite series, and I can do this starting with n equal to 0 here. Then I obtain this term, n equal to 1, I obtain this term, n equal to 3, I obtain to 2, I obtain this term, and n equal to 4, I obtain this term. But now we see that in this term we have z minus z0 to the power of minus 1, and the coefficient in this term is the coefficient b1. Just look at our general expression. It looks like this. So the coefficient in the term multiplied with z minus z0 to the power of minus 1 is always equal to this b1, this residue we are talking about. So this means that the b1 coefficient is equal to minus 1 over 2 to the power of 4. So now I have the general expression for these bn coefficients. It looks like this, and in particular when n is equal to 1, I have this residue given by 1 over 2 pi I times the integral of the function f of z. And now I can find this integral just by multiplying this value by 2 pi I. So this integral is equal to 2 pi I to the times the residue b1, which is inserting the values here, I obtain the value minus pi I over 8.